So the story that I'm going to tell started at the end of last year. It was New Year's Eve, and I had been competing in the Advent of Code. Anybody else here competed in the Advent of Code? Some people. Who finished with all stars? Nobody! Oh, come on. Okay. So I woke up 1st of January, and I was a little bit of a hangover, but other than that, perfect. I've been programming every day up to Christmas for the Advent of Code. Obviously, I usually try to do it in the morning from 6 to 7 or from 7 to 8 before work, finish everything, and start the day. So on the 1st of January, New Year, I was like, okay, it's going to be, I have to kick off. I'm now used to doing this programming, but there's nothing, so I'm falling in a hole here. But then Gunnar posted this, and he said, I challenge you to the 1 billion row challenge. How fast can you aggregate 1 billion rows using modern Java? And this is vanilla Java. You get a single class file. That's what you get. No libraries whatsoever. So flex your SEMDs, kickoff 2022. True coder style, but joining this friendly little competition, submissions until the end of the month. So what is this challenge? You get a file with 1 billion rows. You need to parse this, you need to print out the results, and like I said, we are using vanilla Java here. So everything just plain Java language, no frameworks, no libraries, nothing. What's the format of this file? Well, this file has all new lines, and every time you get a city name, and then you get a temperature. And this temperature is between minus 99.9 and 99.9, just one decimal precision, and there's a small separator between the name and the temperature. So you get 1 billion rows, and you're tasked to, in the end, process everything, print out the minimum, the maximum, and the average temperature for each city. And you need to print it out in this specific format. And non-Java developers will say, why this format? But this is basically if you have a map and you call toString, you get this. And that's it. That sounds relatively easy, but there are some problems if you want to process this as fast as possible. So there was a baseline implementation by Gunnar, and it takes about 5 minutes to parse this entire file. The file itself is like, I don't know, 14, 15, 16 gigabytes or something. Even opening this, going through it, storing the min, the max, etc., takes a while. So he uses files.lines to read everything in a single thread. Actually, here's most of the code. So what you can see in the top one, that's Java record. Java now has records, where you can just say this is a data class which has a min, a mean, and a max. You can add stuff to it, but so in this case, we've created a custom toString method because we need to round it at 1 decimal position. There's also an aggregator, which we use to aggregate all the results together. And this is the entire code. Might look a bit daunting if you're not a Java developer. Anybody here never done Java before? Or are you all Java developers? That's cool. So we start relatively low on the bottom. We do file.lines. This gives you a stream of every new line. Those get split up using string.split, and you get an array with 2 parts, the station name and the temperature. And this all gets collected into a hash map. So how does this work? Well, you can use an aggregator for this. And what you do is you start with temperatures. These temperatures, the first one says create a new aggregator. So if there's nothing yet, it creates an empty new aggregator. The second one says if we've got this new aggregator and a temperature, we need to update it with this temperature. And the second one is if we have 2 aggregators, we need to aggregate to add those together as well to be able to fold everything. So the min and the min still mix, still min, still max, but the sum gets added together and the count gets added together. And if you have the sum and the count, you can calculate the average, obviously. And the results print out, which is a good thing because the format that it requires is actually a map.toString, so this is easy. So I said, sure, Gunnar, 1st of January, I'll take you up on this challenge. Let me quickly try to make something. I'll submit the first pull request, because why not? I can wait until the end of January and hide all my tricks, but let's just get this ball rolling. Maybe people will join, and it will be fun. So I submitted an initial pull request, and I already slashed the runtime down to 2 minutes. I was so pleased. I was like, nobody can beat this. But boy, was I wrong. So this entire contest was done open source. All the pull requests could be viewed. So I gave all my tricks away on the first day. But that's a good thing. You can watch, you can learn, you can adapt, you can experiment. And everybody was getting inspired by other people's code. We were just blatantly stealing each other's code. But that's fun. I learned a lot of new things during this contest. So what did I do to slash this runtime from almost 5 minutes to 2 minutes? A couple of small changes. So the first one, why use just a single thread? You can parse a file using multiple threads if you do .parallel. So that's what I did. Why would I take this string and make a new string array where I split it up? Then you start making a billion new arrays, which is not fun. You can just look in the string, find the separator, break it into 2 parts that way. That's just way faster. We do need a different map here, because we are now using parallel, and we are writing in the same map, so we need a concurrent map to not have collisions there. And in the end, we just take this entire set, we sort it, and we collect everything, and we print it out. Easy. Finished. And I got a bit obsessed with this contest. And after 2 more days, I kept the change log. You can already see the changes I did and the runtime in milliseconds on my machine. But on the target machine, which is a different machine, obviously, which is a machine in the cloud somewhere, I got the runtime down to 23 seconds. So what happened in the meantime? Well, one of the things, so on topic, this is Sir Jackie Stewart, F1 racing driver, and he always said, well, you don't have to be an engineer to be a racing driver, but you do have to have mechanical sympathy. So you shouldn't be, you shouldn't have to take the entire car apart, but you have to know how a suspension kind of works to be able to communicate to the mechanics how to set it up properly. And the same thing is true for programming as well. So if you have a CPU, this is just some sample CPU, you can see it has 4 cores, so older model. And all these cores have their own little dedicated memory, the L1 memory. It's really tiny, but every core has super fast access. They also have a bit larger memory, but this is slower memory. This is the L2 cache, and this is also per core on this CPU. And they have a shared L3 cache. And if you look at the times, this is, again, obviously for every CPU this will be different, but the orders of magnitude will kind of stay the same. You can see there are huge differences between L1, L2, and L3 caches. And if you go to main memory or the solid-state drive or a disk drive, things will take ages. So it's very important to put the right things into the right caches. So one of the first things we did was, why, if there's just one decimal position, why are we working with double values? We can just multiply everything by 10, and then we're done. We can just work with integers, which is way faster. Integer math is just way faster than double math, double precision. So when reading, we multiply by 10, so we talk about 100, which is 10 degrees. Another thing is that we, instead of just reading a file sequentially, we break it into segments. And each processor will be responsible for reading their own part of the file, which is really interesting. So what we do is we look at the amount of processors we have available. In my machine, it's 8. And then we just break the file up, and we need to find like the correct spot, because you can't just start in the middle of a segment. You need to find the end of line. And from there, you can pass on the programming, processing to the next part. And instead of using just regular I/O, I'm using memory mapped files. Who here is familiar with the term memory mapped files? Okay. What you can do in a memory mapped file is that basically you tell the operating system, I want this file to be memory mapped. And from there on, you can just reference the file as it is memory. So you can just say, go to memory address, start a file, and it will be there. Your operating system is heavily optimized, and it can do this memory mapping for you. And this is something Java also supports. So if you say files new byte channel, and then you can have the standard option read, and then you say file channel.map, which is the memory map stuff. And in this case, I get back a byte buffer. Byte buffers are Java's best way to access these raw bytes. Although I am going to break this in a couple of slides. I'm still using the parallel, so every segment now is being parallel processed. They all point to their own specific part in memory, which is, again, the file. Works perfectly. And this is already way, way faster. And like I said, byte buffers are perfect. If you have production code and you want to do this kind of stuff, use byte buffers. But byte buffers still do some boundary checks, which is very good. We want boundary checks, but not if you want breakneck speed. So I decided to use unsafe. I had never used unsafe before, but it is amazing. I programmed C a long time ago. You can do all the dirty tricks you used to do, but now in Java. But let me stress again, Java wants you to move away from unsafe. Don't do this. This is cool for contests, but don't do it in production code. The alternatives are really good. Just use byte buffers. So how does this work, and how do we get this unsafe object? There's a static final field, which in it's the unsafe class. We need to get the unsafe. We make it accessible, and then we get the field. And now we have this magical unsafe object. And using this unsafe object, we can do a lot of cool stuff. So, for example, if we do the memory mapping, we can call .address, which gives us like the address in memory, just along a pointer in memory to the start of the file, which the operating system mapped our file in memory. And then I can just say get byte, and I can read a byte from there. Or get long and read a long value from there. Really cool. Who is familiar with the term SWAR? I had never heard of this, but I was very lucky that somebody on Twitter told me, you should look into SWAR. Because up to this point, I was processing each byte individually, which kind of makes sense, because we're talking about characters, and characters have bytes. Why not do 8 at a time? So SWAR stands for simped as a register, and simped stands for single instruction, multiple data. So how does this work? Suppose we have this part of the file, which is Tokyo minus 18.3, new line, Amsterdam, etc., etc. We can read 8 bytes at a time using a single instruction if we just call, if we call unsafe get long. We read 8 bytes at a time as a long value. And if we do that, it actually gets flipped around, and it's 1 minus and a O equals. This is the hexadecimal value that you end up with when we've read these 8 bytes, and it's in a single long value. Second step is that we make a separator, because what we want to do now is that we want to find the separator between the name, where we need to make a cut, and the temperature. The separator itself is this 3b, 3b, 3b thing. We make one long value that has that. And then we go into this seemingly magical method. So what do we do? So first we XOR the pattern that we want. So we are looking for the separator with the input. And you can already see that XOR basically shows you the difference in binary. And in this case, there's no difference at that specific byte. That's the answer we want, but there's still a lot of junk there. So there's this little trick you can do. So we have the least significant bit, and we subtract it from the thing we just created. And then we, then you get like where we had all zeros, we now get all ones, and we change the bit in front. What we do now is that we end it together with the opposite of the thing that we started with. And as you can see, this is what we end up with, which basically counts the number of zeros that it had. So if you had a lot of zeros, it becomes all ones. And if you had just a couple of zeros, you get a couple of ones and then a zero. And now we can look at the most significant bit, because the only way to get all ones, where the most significant bit is 1, is the case where the thing that we were looking for was exactly the same bits as before. So using just 1, 2, 3, 4, 5 SIMD instructions on a long value, we've checked where the separator is in an 8-byte piece of data. This is extremely fast. So there's one thing left to do. So we check and we get this number back. This number still doesn't say anything because ideally we would want the number 5, right? Because there are 5 bytes, we want the number 5 out of it. So what we do is we count the number of zeros, we divide it by 8, but dividing by 8 is so slow you can just shift 3 times, which is the same thing. It's dividing by 2 is 4, dividing by 2 is 8. So if you do this, you divide by 8 and you get 5, and 5 is exactly what we want. So using just a couple of instructions, you can get the separator. This is extremely fast. My code was still creating a lot of strings, because even if I found the separator, I would extract the string value from this, I would extract the temperature value as a string, and then I would create integer values from that, etc. But you shouldn't be allocating all these strings. We have access to the thing in memory. So we can just read these long values, and we can check if the first 8 characters of the thing that we have is the same as the first 8 characters by using a single long comparator, which is, again, 8 times faster than checking a byte by byte. So I stopped creating any strings until the final printing at the end. Then we actually need to create strings to actually output it. But that's just one time, not a billion. Another key thing that you need to be familiar with is branchless programming. So CPUs have big pipelines of instructions. They are very good in following these instructions, and that's almost never the problem if you want to have a fast program. It's almost never executing the instructions. It's filling this pipeline with the correct instructions and being able to predict which instructions will come next. So it's your code's job to fill this pipeline as fast as possible. But what instruction comes next after an if statement? Could be either. Could be this one or this one. Modern CPUs will just do both and discard the result. But branches are always slow. So we want to avoid that as much as possible. How can we do that? This is a very simple absolute value function. If you go in, if x is smaller than 0, return negative x, otherwise return x. If the CPU encounters this, a branch, it will need to, I don't know, or either take a guess or wait until it knows the result and then can continue. But if you do it like this, where you say, I've got this x value, and there's one bit at the end which says is if negative or positive. If I just shift this entire bit 31 times, I got this entire thing filled with either zeros or ones, which turns it into -1. And if x plus 0 XOR 0 is just x, we don't do anything. But if we do x plus -1 and then XOR with -1, you get a negative number of x. And you can always do this. So you can just fill this pipeline, and it can continue on in a branchless way. This is faster. You don't need to do this actually with the absolute value in Java. The Java compiler is way smarter than we take for granted, so it does this automatically. I'm not using this, but this actual piece of code will come back later. So I didn't write my own absolute value function. I just used the standard functions there. So I wanted to take the things that I learned about branchless programming and put this into my parser as well. So I decided I want to write like a branchless parser to get this string value and get the integer of the temperature. And this is what I ended up with. You can see there's no if statements there, so it is completely branchless. But I'm still using a byte array here. So this is from an earlier version of my code, where I was using byte arrays and byte buffers. So I'm not using any SWAR tricks here. I'm still looking at it byte by byte. But there are some things that are really interesting. So the temperature part, that's either minus or just 12.5 or something like that. So these are the characters that we are dealing with. And you can see that the 1, 2, 3, 4, 5th byte is different for the minus and the dot, opposed to all the digits. So that's an important fact. We can use that. So if we want to see if a number is negative, we look at the first byte. We just shift it 4 places so that that single unique bit is in front. We mask it out, and we flip it. So it's 1 if it's negative, 0 if it's a positive number. And I do similar tricks for looking where the dot position is and seeing if a number is actually, this just looks at the length and the fact if it's negative or positive. So it could be 9.9 or it could be 99.9. So sometimes you have 3 digits, sometimes you have 2 digits. You need to take care of this as well. Usually this is a branch, but we want to have this branchless, so I'm doing this. And then these are still characters, but we want actual values. So if you can see digit 1, we get the byte and we subtract the character 0 to get 0. And if you do that, the character 1 will become 1, the character 9 will become 9. I'm actually not doing that for digits 2 and 3 because that's 2 subtractions, but we can actually do that if we subtract 528, because that's the same thing as 10 times the 0 digit and the 0 character as well. So we saved another subtraction times a billion. Every time you see one of these optimizations, it sounds silly, but it's times a billion. And it's good to remember that. And what we can do is just the first digit times 100 times if it actually has this digit. Sometimes it doesn't, which makes it 0, and we're not using it. The 10th digit and the other digit. And everything together gives us an integer value of this temperature. Perfect. And I was so pleased with this code. It was a little bit faster, not really like incredibly faster, but it was something unique. And then this user, Mary Kitty, posted an update of his code, and he came up with this. It took me a while to actually understand what was happening, and I'm going to try to convince you what it does. So the first thing, it's not using byte arrays. It's just reading this entire thing as a long value again. So it's using SWAR kind of tricks. So if we have this temperature minus 18.3, and then there's always some junk at the end, so there's a new line, et cetera, we don't need that, but we get it anyway if we get this getLong function. And again, it will be flipped in memory if you look at hexadecimal things, so I'm going to keep it as this. So the first line actually looks at the dot position. So he has this dot bits mask, which is just 3 different bits, And it's using, again, the fact that these two characters, these two bits are different in these characters than it is in the digits. So it can easily, in a single line, check where the dot position actually is, and it's either at the 12th, the 20th, or the 28th bit. So that's what we store in dot position. We're going to use that later. So in this case, the dot position is as far as we can, because we have and a negative sign, and we have 2 digits for the temperature, and then we have the dot position. So in this case, it's 28. Perfect. For the sign, we do actually the same thing. We take this number, it's in the 5th bit position that are 0 or 1 if it's negative, or a digit. We shift it all the way to the end, so that the bit that we're looking for is in the negative or positive position, and then we shift it all the way back. So the number we end up with is either 0 or -1. If it's -1, if it's negative, 0 if it's positive number. We keep that as well. This is actually a silly method that takes this dot position, which is either 12, 20, or 28, and turns it into 0, 8, or 16. And this is the mask. So we're going to use this to shift accordingly. We either need to shift the number 0, 8, or 16 bits. Now, if there's a minus sign, we don't want to use the values that are in the minus sign, so we need to mask this out. So this creates a little mask. If there's no negative sign, there's no mask. If there is a negative sign, we mask out this first negative character. Perfect? And now we combine this all together. We just take these final bits. We do that for all the 3 spots that we possibly have characters that might be digits. And we're left with a number that is in this form. So it's a single number. It has 1 digit in the hundreds, 1 digit in the tens, and 1 digit in the units. But we're still not there yet. So in the case of minus 18.3, we would have this number here. So 0, 0, 1, 0, 8, 0, 0, 0, 3. We're close. We're close to the number that we want. We want minus 183, but yet still so far, right? It's there. We can see the digits there, but it's not 183. So if we shift this number, we can align everything on top of each other. That's a good start, right? So if we multiply by 1, that's like the same number. But if we multiply by that different number, that's 1000, we shift the 8, and by the other, we shift the 1. It turns out if you multiply by a single number, which is this number added together, you get basically this. The resulting position there will have all these 3 numbers added together. So we get 1 plus 8 plus 3. Interesting. Still not what we want to have, but we are very close. You can kind of guess where this is going. If you take the first number you multiply by 1 and the second number with the shift, and you multiply that by 10, and the third number, and you multiply that by 100, you get eventually there somewhere with all the junk in between, you get the number 183. And you can actually do that in a single multiplication. And that's basically what the top row says. It's 100 times that shift, 10 times the other shift, and 1. If you multiply by this number, you'll get a lot of junk, but somewhere in there, without any overlap, magical, is the number 183 that we were looking for. Yeah, that. I have no idea how you can come up with something like that. I was really pleased with my Branchless method, but this is so next level. So there's just a couple of things left to do. We need to filter out that specific spot. So we need to shift it and mask it out. And the bottom line, we still have the absolute value. So what we need to do is to apply the sign, which is 0 or -1. And that's what the bottom line does. It applies this -1 to our number, so we get back minus 183 as the temperature. And this is really fast. It looks like a lot of instructions, but again, everything's branchless, and you're parsing this entire temperature string in a single go without making an array, without using strings, without anything. You just read from memory, and you get back the number. So, what do we have? We read the file using memory mapped files, which is really fast. We find and we read the city names using SWAR, so we find the separator. And we have a crazy branchless method that takes this temperature and returns an integer. Now we need to store everything, because we need to aggregate everything at the end. You're probably all familiar with what a hash map is and how it looks like and how it works. Basically, example, we've got 8 buckets here. We have this entry, let's call it London. We generate some hash code. In Java, that's easy. You can just go .hashcode, you get a hash code. We take mod 8, so we know in which bucket we need to dump our entry, and that's where we dump our entry. And then we do the same thing. We end up with the same hash code, end up in the same bucket. And for example, if we have a different city, has a different hash code, but in this case, modulo 3, we end up in the same bucket. So we've got a problem. And what Java does is that it, in case of a collision, it creates this tree-like structure where you can just check the first one, is this actually the thing we're looking for? No, then is it this one, etc. So I started to think really hard, and I asked ChatGPT, how can I make this faster? And ChatGPT said, have you looked at forward probing? I was like, no. So what you do in forward probing, instead of making this tree structure, which is complicated and has a lot of overhead, you just put it in the next empty spot. Which sounds crazy, but yeah, it works, right? So you just put it in the next empty spot, and if that one is taken, you put it in the next empty spot. It's that simple. So I wrote this, created my own hash map. What it does, so when going through this SWAR method, I'm actually using this to update. Is there? No. So I'm updating a hash accordingly. So I can do this inline because I already read it anyway. And then I make sure that the table is actually a power of 2. So I can use an AND operation to get the int value. And then I look in my hash table, which is just an array. If there's nothing yet, store it there. And I'm not using any objects or anything. I'm using one big byte array, and I'm just writing everything in memory. This is called a flyweight pattern. So I've got this byte array allocated. I can just, using unsafe, I can just say, well, first I always write along, then I always write int, 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 then I write a byte value, and then there's the city name. Perfect. No class overhead. This is actually something Java is currently working on. In the new JABs, the class overhead will become very much smaller, and in arrays it sometimes disappears. It's doing this in the background automatically. If there was already something there, we need to check that the string that we have is actually the same as the string that's there. And if it is the same, we update the temperature, we update the min value, the max value, etc. And this is the forward probing bit. It's literally as simple as adding 1 and looking in the array again. And if you make sure that the hash code is properly implemented, you'll probably have no collisions whatsoever, so it's very fast. Although it was illegal in this contest to assume there were no hash collisions. Even if you knew there were no hash collisions, you still needed to check the actual string. Some other this was a Java competition. Some other languages were used as well. People have used .NET, Rust, Python, etc. But they often skip this. So you might see someone say, well, I did it in under a second, but they might have skipped this step, and this is a crucial step. So Thomas, he's the creator of the Graal VM. He was also very actively involved. He said, well, this is ridiculous. My code is currently running in half a second. but it takes like 13 seconds for the operating system to unmap. So these memory map files, really cool, but the operating system needs to unmap everything, like clean everything up. This became the bottleneck. And he said, well, I've got this crazy idea. Is this valid? Can we use it? And Gunnar said, sure, go ahead. And he came up with this. So what is happening here? Our main program starts, and the first thing it does is that it spawns a worker thread. It uses the process builder to actually fire this up, and this one is going to actually do the processing. So it's opening the file, it's doing the memory mapping, and it's redirecting the output back to the main program. So we've got two programs working here, the main and the worker. And the main basically exits immediately, but it's still depending on the stream. So it's still waiting for output of the worker. And at the moment the worker is finished, we close the output, the main process stops. The timing stops. Your time has been recorded. And meanwhile, this worker thread is still cleaning up all the shit, etc., in the background. Felt a bit like a cheat, but yeah, the results were being skewed a lot. Like, we were looking at 13 seconds unmapping. So it was good that we actually did this, and everybody just copied this into their own code and was using the same. So which JVM should you use? Or what language should you use? That's also a valid question, especially here at GOTO. I tried a lot of different vendors, suppliers, from Oracle to Azul to, but basically, it turns out a native compilation using Graal was the fastest way to do this. There was one trick you couldn't do in Graal, which is using the new vector API, vectorization. So some people went that route, and they came really close to the top entries. But it turns out native compilation in Java was still a little bit faster, especially if you let Thomas do it. Because he has all the tools, and he's just looking at the machine code that's being generated. Fun fact, there was also a new release of the Graal VM during the contest, and I'm pretty sure he just fixed some bugs in the Graal VM just for this contest. Until proven otherwise, that's how he won. So how do you do this? There was this small script. For my entry, I set the correct Java version, and I give it some options. Half of them, no clue what they do. Some I can explain. For example, the garbage collection is using the epsilon garbage collection. Who here knows what the epsilon garbage collection does? What does it do? Nothing. It does absolutely nothing. You just fill up your memory, you quit, and then everything gets freed up again. Perfect. We don't want any overhead. This all fits in memory, so should be fine. Yeah, so I'm optimizing the heap space a little bit. I'm trying to get Graal to inline everything. And then we call this native image command, and you get a binary at the end. So you're not working with jar files or class files, you get an actual binary. This is what it looks like. So it goes through this entire process. It searches like the entire space. It fires up your application even. And it looks at everything that's being initialized. And then it makes a snapshot of what's being generated. And this is being put in the binary compilation in the end. One great thing is that you can actually use tools like perf to see the actual machine code. And this is something Thomas was heavily doing. So he was very good because his code, my code was using all kinds of dirty tricks, but his code was really clean because he would just make sure that his Java code would, using the Graal compiler, make the exact machine code he wants. That guy's a genius. And there was also the last week of the competition, I started to notice that any changes I made on my machine, which is an M2 MacBook, were completely irrelevant to what was happening on the cloud machine. And once things don't correlate anymore, you have no idea what you're doing. You have no idea what you're optimizing. But this is basically where I gave up. For a moment, I considered also renting out a cloud server to actually test on that server. But I'm Dutch, and things that cost money, that's not how I roll. So, end of the month. I kept a change log, and you can see all the things I did and where I started out. And basically every little change got some update. This is actually my favorite one. Add a lot of comments, priceless. Because that was key in this contest. Everybody was reading each other's code and trying to understand what was happening, and it was such good fun. And Gunnar is probably going to do another contest early next year. So if you have the time, please join him. It's fun. You can also see the switch where back there I said, well, the scores are getting worse on the target machine anyway. And then I switched to my old MacBook, because my old MacBook has an x86 chip in it, so I could actually use the perfect command there, which is something you cannot do on a MacBook using macOS. So the times became a lot slower, but it was a little bit more specific to the infrastructure of the cloud machine. So the results. I came in 7th, which was I was still pretty proud. And you can see Thomas eventually won the contest. Yeah, 1.5 seconds. So we went from 5 minutes, almost 5 minutes, in my case, to just over 2 seconds. That's how much time you can gain if you optimize your code, which is, I would have never guessed that it went down this far. I always want to give a huge shout out to Gunnar, who hosted this contest. He grossly overestimated the time that it would take him. Every day, like dozens of people would submit a pull request, and he would manually go through them and check if everything was valid. And he didn't have the correct infrastructure to begin with. He didn't have automatic runners when it all started. But it was fun that a lot of community members came in, started helping, and started creating scripts, started creating ways to automatically set up the server, etc. Just really cool. Let's go through some questions.